In this video, we will review Laplace transform. By definition, Laplace transform of a time domain function f of t is the integral from 0 to infinity of e to the power of minus st f of t dt. Laplace transform is denoted by capital F of s. Laplace transform ordinary differential equations from the time domain to the frequency domain. So you go from the t domain to the s domain, and when you replace s equal to j omega, and as you know, j is the square root of -1, omega is the frequency, the time domain expression becomes a frequency domain expression. Now what this does for us is converts difficult time domain integration problems to easy algebraic problems in the frequency domain, and we'll look at it shortly when we integrate ODEs with Laplace transforms. Laplace transform is a fundamental concept for classical controls. Without Laplace transform, you won't be able to do anything in this class. You can describe dynamic systems with transfer functions. So in the time domain, you have differential equations. In the frequency domain, you have transfer functions. Transfer functions essentially Laplace transform of the dynamic equations or differential equations with zero initial conditions. You can analyze stability of systems. You can analyze frequency response and ultimately design controllers. The Laplace transform is a linear operator, which means it obeys superposition homogeneity rules. Earlier, we looked at what a linear function is. This is the same thing for operators. What this basically says is if you have two functions f of t and g of t and two scalars alpha and beta, the Laplace transform of alpha f of t plus beta g of t is equal to alpha times Laplace of f of t plus beta times Laplace of g of t. How do you do the proof? You go back to the fundamental definition of Laplace transform. Laplace transform of alpha times f of t plus beta times g of t is equal to the integral 0 to infinity e to the power of minus st times alpha times f of t plus beta times g of t dt. Now you can take the integral sign inside with this e to the power of minus st. That's how you get this and this. Now alpha and beta are constants, scalars, so they can be brought outside the integral sign. Beta can be brought out here, alpha can be brought out here, and this is how it looks. Now if you look what's inside the integral, and this whole integral then looks like Laplace of f of t. This whole integral here looks like Laplace of g of t, and we have the proof. Let's look at some Laplace transform examples. So let's look at Laplace transform e to the power of minus at. By definition, we have Laplace transform of e to the power of minus at is integral 0 to infinity of e to the power of minus st, and the function dt, the function here is e to the power of minus at. You can add the exponents here like so, and if you integrate this, you know what the integral of e to the power of minus s plus a t is with respect to t. It's this, and then you evaluate the integral between 0 and infinity. At 0, this expression is 1 inside the bracket. At infinity, this expression is 0. That's what you get. So Laplace of e to the power of minus at is equal to 1 divided by s plus a. This is a little bit more complex example, and we're going to look at Laplace transform of sine of omega t. By definition, again, Laplace of sine omega t is integral 0 to infinity e to the power of minus st sine omega t dt. Now we'll use integration by parts. Here u dash is e to the power of minus st and v is sine omega t. You integrate e to the power of minus st, you get this term. V is as is, and then this term here, it's minus integral of u v dash. So integrate e to the power of minus st, and that's this term here with a negative sign. That negative sign with this negative sign becomes positive. V dash is differentiation of sine omega t, which is cos omega t times omega. you get this expression. Now if you look at this first part, this evaluation here, at t equal to infinity, this is 0, so the whole term is 0. At t equal to 0, the sine omega t equal to 0, so the whole term falls off. The left hand side is essentially equal to omega divided by s integral 0 to infinity e to the power of minus st cos omega t dt. We again use integration by parts, where u dash is e to the power of minus st and v is cos omega t, and this is the expression we get. Okay, now notice that this is again Laplace of sine omega t, and let's look at this expression here. Now if we have to put the limits of integration, at t equal to infinity, this term becomes 0, so the whole thing drops off. At t equal to 0, this becomes 1, and this becomes 1 as well. So you'll 1 divided by s of minus 1 divided by s remains. So if you do that, and I have substituted here for Laplace of sine omega t, you can bring this to the left hand side and evaluate the limits of integration. This becomes s squared plus omega squared divided by s squared. This s squared cancels with s squared. Minus times minus is 1, and therefore Laplace of sine omega t equal to s divided by s squared plus omega squared.